Yes. Let's look. Did I make a boo-boo? Minus 4x, minus. Yeah, it should have been positive. So 21, right? Okay, 21. 4x minus 4x, so minus 4x squared. Yeah, positive 16x squared. Okay. So this is being able to give the zeros of complex of a total solution or a complete solution of a polynomial of degree 3. If you fold everything out, it should work out. Sorry. Okay. Here we go. This is what I want you guys to copy down. We're going to kind of do this today. Okay. Rational functions. You guys should be able to see this. Write down the objective. Our objective is to find asymptotes of rational functions. We're also going to be able to identify the solutions to them by looking at the intercepts, both vertical and horizontal. It's not that difficult, but you've got to know the process. You've got to be able to identify, okay, if I'm going to look for the asymptote for vertical line, got to look at the denominators. If it's horizontal, got to look at the leading coefficients and the degree. Okay, something like that. So rational functions, we're going to finish up tomorrow. Wednesday is team test. Thursday, we're doing this career fair thing, so I'm not going to see you guys. I will be posting a review should you choose to do it. It's good extra practice. And then Friday's our test. Friday's our test. So be ready for it. You guys are going to have at least 2 days, 3 days to study. Yes. You are going to keep your team test. You're going to keep your team test. I think at the end of that, I'm going to let you guys, it's going to be a little bit different team test. I'm not going to really count it for this one. I'm just going to give you guys the answer key to it. And I'll probably go over I'll probably do a video on it. But this is how you get this solution. This is how we find this value. This is how so I'll probably run through it for you guys. And I'll make it probably earlier than I need to. Just so you have it for Wednesday. You can review those problems and how I got those. Thursday for the career fair, I'm going to give you another posting of a review, just an extra CUDA kind of something, just an extra worksheet. That's going to, because Thursday I have my final game, so I can't even be here after school. So I want to try to prepare you guys as much as you possibly can without me being here. I know it's kind of double standard, but I don't want to get too far behind because the next couple of weeks are going to fly on by. Yeah, they are. Because even on the 10th, so we go into November in this first week. On the 10th, which is that next Friday, we have off. So we have the 10th off. And then we come back for a full week. We go to Thanksgiving break.
How long is Thanksgiving break?
1 week. Yeah, 1 week. Then we come back. That leads us into December. We come back for 2 weeks and we're done. We do our final. We do our semester test. Okay. Here we go. So let's talk about this. We're given a rational function. A rational function is basically two polynomials over themselves. The n of x represents the numerator of the polynomial of the numerator. The d of x represents the denominator, meaning on the bottom. They're polynomials. D of x and n of x are polynomials. An asymptote, which we got to be able to explain, is a horizontal or vertical line which the graph is undefined, meaning the graph will never cross them. That's a basic idea of them. I believe we talked about them last year, especially with exponentials. Some of you guys, some of your teachers went a little bit more into depth of looking at rational functions. So we got to be able to talk about them just in the basic understanding of them, okay? So we got to be able to kind of explain to them how to graph them and what their properties look like. Finding the intercepts and finding the horizontal and vertical asymptotes are not that difficult, but we got to be able to explain that. We got to be able to show what that means, okay? And all we're going to really do to kind of graph these types of functions instead of looking at shifting them is if you can identify the vertical and horizontal asymptotes, that's easy. Looking at the intercepts will be easy. And then plotting just a couple of points around our asymptotes will kind of give us a good understanding of what the function will look like, okay? So not hard, but you got to remember some of the stuff. Okay, we got to look at these type of values, and we're going to kind of explain to you what I mean by that in a little bit. But we got to be able to explain that. Okay, so keep that in mind. You have the handout. You have the handout in front of you. Use it. Definitely use it. Okay, it's going to be helpful for a little bit because I do want to cover a bunch of these type of problems. Okay, so here we go. This will be posted by today just to give you guys a better understanding of this. I'll post this at lunch. Asymptotes. Okay, one thing that I want you guys to take away on that graph to the right, if you guys can graph our parent function of a rational function. This is what the function actually looks like. Okay, it looks like an x that has both asymptotes at certain values. One thing that I want you guys to write down in that little box to the right is that when x is equal to a number or x is equal to 0 for this, we're given a vertical asymptote. Meaning a line that's going to be vertically is going to go up and down on my line. And this asymptote can change depending on the value of our x-intercept. It's usually going to be where x is equal to a number. And we've got to be able to put that in a context type of problem. So x will be equal to a value. We're going to describe that when we're setting x equal to 0. Okay. If we're looking at our parent function, we do 1 over 0, where x is equal to 0, and that's undefined. So that would be a point in which it's undefined for us. If we do it the other way, in which we have a horizontal asymptote, will be when we have a y value equal to 0 or y value equal to a number. And again, we're going to discuss that. Again, asymptotes are lines, are these imaginary lines that the function will never cross. These are the function values that they can never take on. So we do want to be able to explain that in the context of graphing problems. So keep that in mind as we do them. Again, you guys have the handout that's very closely assimilated to it. It's on the back side of this part. Okay, it is there. Definitely want to use it. You guys can. Okay. Understanding the closer, as a fraction, the closer you are to 0, or if you do a fraction, the larger the number will get, right? Because you multiply by its reciprocal, vice versa for a negative number. Okay. The smaller the number is between 0 and 1, the larger it becomes. The larger the number becomes, the smaller the value would be. 1 over a million is a very tiny number. Okay, that's why it approaches the further you go down. The further closer you get to 0, 0.1, 1 over 0.1, or 1 over 1 in 1,000 becomes very, very large. So we're looking at these exponential types of functions, not really exponentials, but we're looking at fractional types of problems. Okay, so we're going to look at these critical values. You know, especially at 1 and 1, we're going to have certain values in which gives us good values for these, but we'll talk about that tomorrow. Here we go. Let's keep on going with this idea. Okay, we have several different types of ways, and we're going to kind of get to this. You don't need to copy this down. A rational function can have vertical, horizontal, or slant asymptotes, and we got to be able to look at those. They're not that difficult to understand, but we got to be able to look at the 3 different categories, because I can pose a question to you: what type of asymptotes will we have? Vertical, horizontal, slant. Will we have them both? Will we have only one of them? Will we have none of them? So it is important that we talk about these. Graphing rational functions. Okay, you guys do not have to write this one down, okay, because we're going to cover that in these next couple of. Find the asymptotes and graph them as dotted lines. So that's how we're going to look at them when we're graphing them. We're then going to look at the intercepts, so we're going to find some points. Okay, X and Y tables. We're going to go ahead and create those. We're going to make it very simple. So as long as you have a calculator, you're going to be able to plug these values in roughly where we need to find them. Then we're going to look at drawing the curves of where these should go, especially if we know they don't touch the line or they don't cross the asymptotes. We're going to have a good rough value of where these values are going to look like. So don't worry. You don't need to copy this. You don't need to copy this. Okay, because I want to get to these type of problems. Finding the intercepts. Now above this little line, if you guys can, I know it kind of says right here. Above these little lines right here, above that little line, can you guys copy down those 2? Okay. Doesn't need to be perfect, but right where my two fingers are, copy that down. Copy down the top, because you will need those. It's important that we're understanding. Okay. To find our intercepts, these are points in which they cross the x and y axis. We need to be able to look at where y and x is equal to 0. And we're going to look at 3 different cases. Sometimes they're going to cross at 2 points. Sometimes they'll cross at 1. Sometimes they won't even cross at all. So we want to be able to identify those types, okay, and how we look at them. Okay. And all we're going to do, and I'll do this top one, is we're going to set y is equal to 0. When y is equal to 0, we're given an x-intercept. When we do it the other way, when we say x is equal to 0, we're given a y-intercept. And so this is where you guys, they're not that difficult to do, but you got to be able to apply them. Okay, and we'll look at these 3 different examples of seeing how many times they intersect our axes. And I do want you guys to put them, because I'm going to give you a problem like one of these, or give you a rational expression and go, what are the asymptotes? What are the intercepts? Plot me a couple of points, graph the function. Done. Vertical, horizontal slopes, what kind of slant asymptote? So we're gonna cover that. I'm going to kind of erase these bottom ones for us. I'm just going to kind of do this in 3 different parts so you guys can see what I'm doing here. And I'll do them according to the colors you guys see. So in blue, I'll do our x-intercepts. Our red, we'll do the other ones. For our x-intercept, we want to be able to say y would be equal to 0. Therefore, we're going to get an x-intercept. If we do our first case, if we set y equal to 0, we're going to get 0 is equal to x plus 4 over x minus 2. We got to be able to solve this out. Luckily, this looks actually really nice. What happens if we multiply both sides to get rid of that denominator, x minus 2? What occurs? We're basically going to get x minus 2 to get rid of the bottom, our denominator. These are going to reduce down. What's anything times 0? 0. If we subtract out 4, x is equal to 4. Our intercept, our x-intercept is going to be at -4. Done. Usually when you set y equal to 0 for a rational function, the bottom will go away, because how we're going to multiply these out. So we get an intercept at -4. If we do the y-intercept, or x equal to 0, we're going to get a y-intercept. And we set y is equal to 0 plus 4, 0 minus 2. We're going to get 4 over -2, or y is equal to, kind of nice, right? This will be our y-intercept. We have 2 clear points in which they intersect at our lines. We have one at -4 for x, and then going down at -2. So these are 2 easy points. It's going to help us graph it. We know it's going to have to cross at those 2 points. Done. That's it. Okay. So this is a case in which we have both an x and y intercept. Okay. There are some cases in which they might not intersect, depending on the type of function we have. Okay. I'm going to kind of erase this so we can kind of do another problem. Let's look at our other case. Let's look at our middle one now. So this is our middle one. And we're going to do the same process here. If I wanted to do my y-intercept, then I'll be doing my y-intercept over here. Y is equal to 0 for an x-intercept. If I set y equal to 0, we're going to get this. What happens when you multiply both sides? What essentially happens? The bottom goes away, right? So when the bottom goes away, we're going to get 0 is equal to 2. Is that even a valid answer? This is bad. This is bad. If you don't have an x equal to the value, if you don't have something, this means no x-intercept. Meaning it does not cross the x line. No matter where you graph this, it does not cross the x line. If we were to graph this quickly, just a small little idea of this, that on my x-axis here, that function will never cross. That's going to be our asymptote for it, essentially our asymptote. Doesn't cross at that point. If we do it the other way, where we're looking at our y-intercept, we're going to do x is equal to 0, y is equal to our intercept, y is going to be our intercept. If we plug this in, y is equal to 2 over 0 minus 2. We're going to get 2 over negative 2. Or what? Y is equal to negative 1. That means we're going to have an asymptote at negative 1. Sorry. Oh, I made a boo-boo. It's not a vertical line. So this is not a vertical line. We've got to look at it this way. My apologies. It's not going to cross our, I'm sorry. Let me just do it that way. We'll look at graphs tomorrow. I'm not going to confuse you. I'm confusing myself right now. So we have a y-intercept at y is equal to negative 1. Make sense? Okay, this is a case in which we have one intercepts of that. Okay. Our last and final case, we're going to look at another version. So 0, 1, or 2 different cases. So for our last case, we want to be able to look at this function. We're going to say y would be equal to 0 for an x-intercept. When we set y equal to 0, we're going to get 0 is equal to x squared plus 10 over 2x. What happens to the bottom, essentially? Cancels out, goes away, so we're going to get 0 is equal to x squared plus 10. If we solve this out, we're going to subtract 10 from both sides to get x squared. X was going to be equal to plus or minus the square root of negative 10. What tells us about that? What is that? Complex. Can we graph a complex number on a real line? No. So no x-intercept. Meaning it's not going to cross our x line. It's not going to cross the x-axis. It doesn't cross it. Nowhere will it go between there. If we do it the other way, where we say x is equal to 0 for a y-intercept, and we're going to get y is equal to 0 squared plus 10 over 2 times 0. What's anything times 0? So 10 over 0. Is that even a valid answer? So again, this situation would be undefined, so you would have no y-intercept. So it doesn't cross the x-axis, and it doesn't cross the y-axis. It's going to look kind of funky. From my understanding, I believe the way that this is going to look, and if we're graphing this as a rough case that we can have, I think it's going to look something like this. Doesn't cross the axis. It bends back around. Okay, and we're going to look at these, and we're going to have asymptotes. It's a slant asymptote on this one because the degree is higher. We're going to look at that. Don't worry about this. Okay. So that's how, is this hard to find for our x and y intercepts? Not that difficult. And we're going to practice this more and give you more problems. Okay. Let's look at continuing this idea. Now, to find a vertical asymptote. So we found our intercepts. We should be able to do that. Set y and x equal to 0 to find where they cross our y and x axis. Sometimes we're going to have 1, many, or none. Or 1, 0, or none. 1, 0, 2, none, 1, or 2. Sorry. Finding the intercepts. Okay, our asymptotes, sorry. Vertical line in which the graph does not exist. Given a function, a rational function, n over d, the name of our d. Vertical asymptotes At zeros of dx, write x is equal to a number. This is where it's going to be our value. Our examples that we're going to look at are these two. And we'll look at these where our values are. Giving you a little heads up on these, a quick way to look at these is let the bottom polynomial equal to 0. Solve for x. X equal to a number will represent your asymptote. So to solve for these asymptotes are not that difficult. These are going to be vertical lines in which the graph will not cover. Now I think this one is probably the easiest one to do out of all of them, because the only part that you need from both of these equations is the bottom part. That's exactly what we're going to look at. Is it hard so far? There's a lot of information to go over, but if you're looking at these homework problems and you're given these outlines, just look at what they're asking you to do, and you're done. Vertical asymptote, vertical line. Okay. If you're ever getting confused on what a vertical asymptote is, I always think of vertical, so I'm going to kind of draw this on the side. If this helps you out, by all means, please do it. For vertical, some kids have the difficulty remembering. I always think the vertical always represents this V, which is like at the beginning of an arrow, right? It can go up and down like that, and you can just make it like that. It's a dumb way to think about it, but if it makes sense to you doing it that way, some people are getting confused on horizontal, vertical. Hey, whatever works. Do you, boo-boo? Do you? Okay. Now, looking at this, what we want to be able to see here is our bottom denominator. So what we're going to look here is the only thing that we need down below is our bottom portion of this to find a vertical asymptote. It tells we're going to let that bottom denominator equal to what? So 2x plus 3 is going to be equal to 0. I'm not going to show my work because I believe you guys can do this. 2x is equal to negative 3. X is equal to negative 3 over 2. This right here is our asymptote, our vertical asymptote. This is vertical ASYM. That's our asymptote. Easy? All what you need. You don't need the top part. That's going to be up for our horizontal. We don't have to worry about that until our next bit. Looking at the one to the right, let's look at this one. What do we need? The top or the bottom equation? The bottom, again, is going to be x squared minus 4 is equal to 0. So we need this. Solving this out, we're going to get x squared is equal to 4. Oh, what? X is equal to plus or minus 2. How many asymptotes do I have with this one? 2. So x is equal to 2, and x is equal to minus 2, or minus 2 and negative 2. These are going to represent our vertical asymptotes. We can have 2 of them. It's okay to have 2. We're going to look at 2 of them. It's okay. We sometimes can get functions that do this. In a quick reference, this is not this problem here. But let's say we have, this is our vertical asymptote here. We can get a function that just does like this. Or that's a horrible way to do it. Something like that. For this other type of asymptote where we're given 2 boundaries, it can look something like this, where it goes up. It can look kind of weird, where it splits it into 3 different graphs. So it is okay to have 2 asymptotes on this. Okay, don't worry about that. We're going to graph it tomorrow. Don't freak out. Okay, in this case, we have 2 or 1. Okay, easy to find the vertical asymptote, right? Set the bottom equal to 0. Solve it. Next value. Okay. For our other case, horizontal. This is the one that you want to be able to look at and solve out. Again, given a rational function, numerator over the denominator, horizontal asymptotes are based on degrees. We got to look at the degrees. If the top one is bigger than the bottom one, or the top one is smaller than the smaller one, we're going to get our horizontal asymptote at y is equal to 0. If they're the same, we're going to look at the leading coefficients. And we're going to do an example of these, so don't freak out. I got you. So copy down that. Copy down that. I would definitely recommend you copy down this version. Basically, we're going to have an asymptote of this if you have small degree over large degree. Small over large. Looking at this example problem, we have a degree of 1, and you always want to take the leading or the highest degree. In this case, it's 1 over 2, so it's small to large, small over large. That means we're going to have an asymptote at y is equal to 0. A small quick graph of this would mean a horizontal line at y is equal to 0. It's going to be on our line. Just quick, I'm not going to graph anything but our asymptotes. If they're the same, we're going to look at the leading coefficients. That means same over same. Same over same. That's going to help you remember it. We're going to look at the leading coefficients. In this case, we're looking at our example here. This will be 3 over 3. If they're the same, we've got to be able to determine our leading coefficients. So this would be y would be equal to 4 over 2. So 4 over 2 would be what? Y would be equal to just 2. This would be our asymptote for this value. It would go, I can't even graph this one. Quick function of this would be at 2. Something like that. And again, don't worry about graphing it today. We're just going to pull the information from it. The last one we're going to have to talk about. So this is the last case. We're going to do 2 cases of these and then the bottom one. If the large over small we're going to have a slant asymptote, a possible slant asymptote. Large over small. This means that our polynomial in our example is 3 over 1. Large polynomial over a smaller degree polynomial. Again, horizontal depends on the degrees. Okay. It's a lot to cover, right? 3 different things. We talked about intercepts, setting x and y equal to 0. Then we talked about vertical asymptotes, which you set the bottom equal to 0, or bottom equal to 0, solve for x. This one we got to look at the degree. So there's 3 different things. They're not that difficult. Not that difficult, but you got to be able to see where they're going to lie. Okay. All we're going to do to begin with is we're going to, because I want you guys to practice doing these vertical and horizontal asymptotes, so we're going to do them both together at the same time. But we just want to be able to identify them, and I'll do one in one color, do one in the other. Okay, they're not that difficult. This is why graphing rational functions is not too bad when you understand what you're looking for. So here we go. Let's look at these examples. Now, you guys don't need to copy this down. You guys already have this down on the information, so we're not going to go ahead and do that. Let's see if I jump to this one. These are the examples we have. You guys have them below, right? We have them below? Okay. We got to be able to determine the vertical and horizontal lines, these vertical and horizontal asymptotes. For our vertical ones, I'm going to go ahead and do in blue. Find the zeros of the denominator. So I'm just going to say let B be our vertical asymptotes, our vertical asymptote. We look at the bottom for this, right? X minus 3. What would make that 0? 3. So our vertical asymptote would be x is equal to 3. Done. I don't need to do that much work to it. You don't need to solve this out for this type of problem. If you do this on the test and you put this, I'm fine with that. Okay, because there's bigger fish to fry. As long as you're able to understand that, I'm okay with that. You don't like fish? No? Yeah. A little mahi-mahi. Okay. If we do this type of function, and we're looking at this example, we're going to do the horizontal now. Horizontal deals with our degrees of our polynomial. Looking at this one, what do we have? We have 2 over 1. What type is this? What kind of category? What type? It's large over small, so that means I'm going to have what? A slant. So I'm just going to put a slant for this one. We are going to find out what does slant mean. What does a slant mean? But just put slant for the time being. We have a slant asymptote for this. I'll show you what I mean by that in a little bit, because it does take us to do, we have to do a little bit more than that. Okay? It's not just like slant, we're done. We've got to be able to express it, because we want to be able to graph these. So we need to graph the slant one. So we're going to look at that. That one's kind of our harder case. So I just want to get that one out of the way before we do bigger ones. Let's look at again. Let's look at the next type. Let's look at our next example. And we're gonna do this one. So looking at the bottom one, we look at the denominator. Can you solve for zeros for that? Our vertical asymptotes for x squared minus 1, adding 1 to both sides, taking the square root, we're going to get x is equal to what? Not just 1, plus or minus 1. Okay, we're going to have 2 asymptotes for this. So this is our second case that we can get here. This is our second type of case. Okay, again, solving for 0, I think you guys can do that by now. For this bottom one, our horizontal asymptotes comes from the degree of the polynomial. So we're going to look at, this is going to be 1, this is going to be 2. What do we have? What kind of scenario? Small to large, which tells me I'm going to have what? Y equals 0. No real work that you have to do with these first 2 cases. Okay, this means we're going to have a horizontal line at y is equal to 0. We have both of our asymptotes, so we have a rough estimate of what this is going to look like for us. Okay, and I'm just going to give you context to these problems, and this is what we're going to kind of allude to as we're doing these. And I'm going to kind of just give you rough graphs of these. I do not know the exact graphs of these, but I just want to show you what they might give us. We have it at 3. Let's say this is 3. We have a vertical line here. And then our slant asymptote for our horizontal will look something like this. So it might look something like that, where it's going to be in one of those quadrants. In this case that we're going to get here, we're going to have it at -1, +1, and we're going to have a horizontal line here. So we have 6 quadrants that can be in. And if we look at that last case, let's look at our last case and do this one. To solve for our vertical, what's the easiest way to find the zeros for this type of function? Factor. We always want to be able to look back and factor. What's this? The snowflake, right? The cross, right? I got what you're getting at. So we got to be able to factor this out. So look at chapter 1 coming up again. Welcome. You're going to see it a lot. You got to be able to factor these guys. So we're going to kind of cross multiply. -12 up on top. 2 x's on the upper sides of these, what adds up to give us -1. What 2 numbers give us -12 adds up to give us -1? 4, positive 3? Yeah. Other way, it's okay. You got it. In this case, we're going to get 2x plus 3 for one of ours. And this one's going to be x minus 2. So our zeros from this are going to come from our value. So it's going to be x is going to be equal to 2. And our next one will be what? Negative 3 over 2, right? Just solving those out. We should be able to do those without really showing that much work to them. Again, just setting them equal to 0, right? So are these difficult to do? No. These are the types of cases I'm going to give you. This is about as difficult as I will give you them. Okay? Are we okay with that? I figure, I'll probably tell you on the test or not, hey, you might want to factor this type of problem to find for the verticals, okay? And if you guys have a question on that, just let me know. I'll be more than happy to assist you because we're not spending too much time on these. Our vertical or horizontal asymptotes derive from our polynomial. What type of scenario do I have with this one? They're the same, so what do I have to look at? The leading coefficients. What are my leading coefficients for the top one? 4 and 2. So that means it's going to be what? Y is going to be equal to 2. Done. That's all we wanted to do today. We have one more thing. I apologize. We have one more thing. But this is the same idea. Now the last part of this is just an extra addition. It's not that difficult. It's extra practice. We've done a lot of these already. Okay? Cool stuff, guys. So far, so good? Okay. So this is how we want to be able to find our asymptotes for these. Now, looking at our next one, this is the kind of the last type of thing. You guys can try these out a little bit later. These are the asymptotes that you're going to arrive from getting these. And the PowerPoint kind of messing up right now. Okay, so this is our vertical, horizontal. These are the different types that we can identify. Okay. It's not going to have one, but we caught it as a slant. We'll count our horizontal as a slant one. Now, here we go. For our slant scenario, in the event that I give you large over small, this is for polynomial that's 1 degree more than the degree of the denominator. And these are the type of problems I'm going to give you. Essentially, what we're going to look at is, if you guys are seeing it on your paper, is I want you guys to be able to just use synthetic or long division to get our quotient and remainder. The quotient, that last bit apart, will be our slant asymptote. It will be the line that will be created that we also have to graph. And I'll show you what I mean by that. We're going to graph more of these type of problems where I just want you to give me the equation that represents this slant asymptote. It's not really a horizontal line. It's not, well, we're going to count underneath that category. It's not the same. Horizontal means horizontal, but a slant, horizontal slant, that doesn't, yeah, horizontal slant will be, that's a far stretch. Your college professors are not likely going to teach you that way, but it just makes more sense to say it that way. Okay. So we're going to look at just 2 examples, and I'll give you guys your homework. Are we cool with that? How much more time we got in this class? 4 minutes? 5 minutes? 4? 3? 2 now? So I'll just do 1. Okay, 1. Thank you. Keep me posted. Okay. Good time to go in this class, man. Gotta get through the material. Okay, so here we go. Because I want to be able to get through this last part. Oh, go back. Really quick on this one. We definitely have a polynomial with degree higher than the one down below. This is large to small. I'm going to show you both ways you can get them for this type of problem. For your polynomial, if we divide it, taking it the long division way, and some people prefer this, doing the long division, we're just going to get x squared minus 3x minus plus, reducing. Sorry, I'm kind of rushing through this, guys, but I want to write these down. Then we're going to get minus 1 here. So minus x plus 3. This will be plus and minus, which will just give me negative 2. Or negative 8, sorry. The only thing I need, because it's a slant asymptote, is my top values here. The horizontal asymptote will be for my quotient. Or in this case, let me just write it out. Y would be equal to x minus 1. Y equals mx plus b. We're going to be able to graph this. That is an asymptote. I'll do this for do not tomorrow as well. If we do it the long division way, the long division way works as well. We're going to use 3 on the outside, 1, negative 4, negative 5. We're going to take, this is our remainder, our quotient is going to be 1 degree less. So x minus 1 will be the same. So our horizontal will be, y would be equal to x minus 1. These come from the same thing, the same exact ones. Okay? So we're going to talk about what does it look like to graph these. Here you go. Here's your homework. Sorry. There you guys go. Take a picture of that. I would like for you guys to try all of them except 15 because you guys cannot see it. This will be posted today on School Loop. PDF, I'll give it to you guys PDF style or JPEG, sorry. Bye guys. Bye guys.